Hello, good afternoon, good morning, good evening, wherever you happen to be around the world. This is Dr. Mohamed Nezami. I'm an RF circuits design consultant, a freelance consultant, that is. I design active and passive components. If you have a need for um, an RF design, I can work with you from concept to Gerber files. Today, I'm going to continue. This is the third part in the series of flat panel antenna array feed networks. I have been discussing antenna feed networks for microstrip array antennas. I did cover two parts. These two parts, you can refer back to them on my video YouTube channel. Basically part 1 and 2 here. I welcome you to go ahead and view, watch those first. And please, if you don't mind, please subscribe to the channel and hit likes on those videos. It helps out in spreading the video audience larger, which to the benefit of many. I have 50 plus videos on RF components, design and modeling. You can refer to these. Now, in addition to the concept which I'm talking about today, I did cover about a year ago or 2 years ago, the radial power combiners and splitters. This is a concept that is also related to antenna array feed networks. You can refer back to these videos if you're interested. Now, these combiners are different than the combiners we're going to cover today, which are basically the Wilkinson dividers and the T-junction dividers. And so today, let's go ahead and I operate out of Jerash, Jordan. Jerash is the city that you see in my background here. It's an ancient Roman town. You're welcome to visit it if you like, if you're interested in history. Again, my consulting rate is very reasonable to those in the United States and Europe, since I work in this part of the world, which is much, the standard of living is much lower than it is in the Western Hemisphere. You can reach me at this phone number or via this email. Okay, so let's get today, let's continue this. So I'm gonna put this, minimize this guy here and get going with this. Okay, so today's concept is a third part in this series of flat panel antenna systems. And as you know, flat antennas have become very common nowadays, and even more common so with the integration of the RF front ends into them. You probably some of you have these terminals from Starlink. These are basically, and it is an example of an antenna array system, which is very interesting. It's circularly polarized and it's got dual feed, vertical and horizontal, which is interesting. Also for 5G, these flat panel antennas, you can see them popping out in cars for radars, 360 radars. A lot of them have these panels. The antenna feed is basically divided, even though we did not introduce it, this is the beginning, but there are several types of antenna element feeds, okay, you might say. And these are basically, some of them can be as simple as coaxial feed, which comes in from the bottom. There's a clearance hole for the center pin that connects to the batch on the top. And the shield, of course, the outside, the outer shield of the coax connects to the bottom, which is the ground, okay? And it can be also using microstrip line feed, just like in here. okay? This is a line feed, which we will show in a minute. Examples, which we have shown already in the last two videos, many examples of these. And this is approximately coupled feed, where the line is not physically the feed lines are not physically connected to the batch, but near vicinity, and through some careful design work, this works out. And then the most common one that nowadays have been used is the aperture coupled feed. Literally almost all of these systems that you see use coupled feed. As you can see here, you don't see any traces for the feed network on top. It's basically, well, this one is, you see them on top. This is a microstrip feed here. But the other ones, like these ones, the feed network is basically through an aperture coupled feed. And that is basically shown here, where the element is on top, and then you've got a ground plane with a hole in it with a slit, a rectangular slot, and then a feed line that comes in at the bottom and leaks the signal out to the batch. Here's an example on microstrip line feed, just a couple, run by you a few of these examples. We have shown these already in part 1 and 2, but just to link up with the thing. So as you can see here, the feed network is all planar on top. And so one of the disadvantages of this, of course, is that you get some kind of little radiations from these lines that in some cases distort the pattern. So a lot of people would rather put these in a substrate on itself and as a strip line layer. And that's what you see in here, okay? What you see in here, there's missing part in here, which is the aperture layer, okay, in here. All it is the ground with a bunch of aperture windows. So you've got the elements on top, and then you've got the feed network in here with lines like this, and they leak the signal through this slit in there in the ground plane, which is not shown. That would have been here, okay? Now, the procedure to design a feed network, basically, or even an array of antennas, I'm not trying to give a lecture on antenna designs, but it is related, so we might as well introduce the concept, just a general concept, is you design a single batch or a single unit cell. Okay, so you have these layers. Basically, you have the layer that have a feed line, and then the aperture, which has we design it based on dimensions that will couple the signal through to here. And this is a batch on top. Once this works, you model this. Once you're happy with the radiation pattern, with side lobes, gain, and so forth, then you replicate this into an array that you have predetermined already what the array aperture should look like, okay? And once you do that, of course, you do replicate also the aperture coupling network. Now the feed, of course, you design it like this, and we have been going through these designs in the last video number 2 of this series. I've shown the principle of designing the feed network using T-junctions like it is shown in here. And we focused on the tapered feed designs, and this one's here, you can see that this here, the transmission lines are all equal width, so meaning they're all equal impedances, except the transformers, of course. So at the feed point to the element, all the lines are the same width. So this means that this is uniformly fed, uniformly illuminated antenna array, in which the side lobe is at best is minus 13 dB, dB below the the gain, the maximum gain, or the maximum directivity. So last time we covered how you design these T-junctions, for both uniform and non-uniform. And that's what we did last time, is we took the array factor of a panel. Okay, this equation here is for the linear array, but for planar array, you just add another term, because all it is array factor for planar is 2 of these that are orthogonal, you multiply them. So you end up with A, N, and N. You end up with an index, which is N and M for the X and Y. And last time we did show how you would get the coefficients depending on the number of unit cells or elements in the antenna array. There are some coefficients that are pre-computed to do the tapering, whether it's Taylor or whether it's Chebyshev, depending on the side lobe level. For instance, in these cases here, this is minus 26 dB for both of them. And we can come in here and you're going to always feed the center element, the maximum signal that's straight ahead. And then, of course, you would taper the signal down to according to a polynomial coefficients that are derived either from tables or from MATLAB. So the most common ones are basically either Taylor or Chebyshev. There's polynomial tabling as well. That's the Pascal triangle, which is also being used. So how do you implement these coefficients, this tapering for the antennas in here? Of course, what you would need to do then is you would need to vary the power ratio for these elements based on these coefficients in here, okay? And that's basically what you see in here. What you end up with is unequal T-junction where the split is unequal power, and this power ratio between the two outputs between the elements, the power that gets to these elements, okay, is based on these numbers in here. And I did show the methodology of how you would obtain these, design this T-junction so that then you can actually replicate it. Same thing for Wilkinson divider. Basically, you end up with a Wilkinson divider, which is an unequal power divider. And that's basically what you see in here. You end up with one side of the divider, the impedance is lower than the other side, okay? And that the width ratio in here is directly proportional to the power ratio between these two outputs. Okay, so now this procedure can also be seen in MATLAB. You can go to MATLAB and if you're using MATLAB, you can, if you have the phase array system toolbox, you can actually go in and it lets you design the array with a specific characteristics, and it even calculates the location of these elements. You could do rectangular, you could do circular placement, okay? So you end up with all these calculations, and so this is very easy to use and very simple. And so and you could do like the Taylor windowing. You can go in there and basically calculate the coefficients and even get a plot of the window and the side lobes, okay, so, and so forth. So let's see what else you can do. Well, you can explore that yourself. Now let's go today and zoom on the Wilkinson divider in antenna feeder arrays. The reason we're interested in Wilkinson is because, as you know, Wilkinson are basically a divider that is fully matched, and it has a decent isolation. So between the antenna elements, for mutual coupling and for interaction between the elements, if you can afford real estate and the complexity, you can, and if you can use Wilkinson divider, then obviously it outperforms the T-junctions. But nevertheless, from what I've seen, almost 95% of the cases, people end up actually using the T-junction, okay, despite the fact that it's unmatched. Then so today let's cover the principles. I know there's a lot of videos and basically Wilkinson divider. I'm not trying to teach you Wilkinson divider in here. The basic concept is basically, I'm assuming that you're familiar with it. I'm trying to basically just explore the usage of Wilkinson divider in the antenna array feed networks. But it's covered in books and basically RF courses. But just to introduce you and for refreshments on the Wilkinson divider. The Wilkinson divider, you can see variety of shapes and ways, different ways of implementations, but all of them follow the principle of a quarter wave transformer section, okay, which is basically you're all familiar with. So they can come in where they can have a straight implementation like this, okay. They can be rounded, okay, or they can be meandered like this, so that you know you can either get it narrower or get it narrower horizontally or vertically, depending on the situation that you encounter. So, okay. Now even though we tend to design arrays with planar printed Wilkinson dividers, and by the way, the passive components, which is the 100 ohm in this case, if it's single section. This here is, I'm assuming right now we're dealing with surface mount, basically mounted on top. In a lot of cases, this is actually implemented with a strip line technique where the resistor is actually a Tizer material or a thin film resistor implemented. So in a lot of cases nowadays, there's a lot of companies that are starting to come out with Wilkinson dividers for various RF applications where they implement them on high dielectric constant, low loss substrates and ceramics. So you can see them coming out like this, or even in QFN packages, like this one from UMS. These ones here as an example from Knowles and Smith Interconnect. So you can purchase these nowadays in frequencies up to like in the millimeter for 5G and 6G and SATCOM, K-SATCOM stuff. Okay, so like I said before, the implementation of the this is a general representation of, say, 8-element linear array feed network using Wilkinsons. They can be completely Wilkinsons, like it is in this case, or they can be mixed. Some people can realize that we can use T-junctions up to the point, and then right at the elements themselves, we use Wilkinson, which now in this case, of course, you get better isolation between the elements. Okay, so you get nicer axial ratio, mutual coupling, and so forth. Now, for planar topology implementations, it's the same thing basically. So we get the coefficients from the Taylor or Chebyshev polynomials for tapering, and then we just basically go in and design this unequal power divider Wilkinsons all over the place to feed to these networks. So let's start with an example, just illustrating the design of this, just basically back to basics. This is how we implement a Wilkinson divider, basically. We've got an input impedance and then output impedance is here. And in between, we've got a quarter wave transformer that transforms the parallel combination impedance in here to match with this one. And you've got the resistor in here. Now, there is a set of equations. These set of equations based on the power ratio between the output 2 and output 3 in here, then we can come up with these impedances in here. And these impedances in here, like I show in the cartoon here, you end up with low impedances sometime, with a high impedance. And then, of course, this additional lambda quarter line in here, that's just in case your output is not 50 ohm, is not ZO. In a lot of cases, if you're 50 ohms in here, you end up ZC and ZD are basically 50 ohms. So we get these equations in here, and if you say, if you implement them for a ratio of 1 between this port and this port, you end up with the very common Wilkinson divider that you see equal power, which is these lines in here are equal impedances. They're 70.7 ohms, okay? And the resistor is 100 ohm. Now, as an example, if you take unequal Wilkinson divider for like where the ports, port 2 is 1/3 of the power, and port 3 is 2/3 of the power. And now we compute these values in here, and that's what they are in here. And I'm going to show that in a minute. Just basically, this is just basically this is these equations. I programmed them already in here, so that let's say that you want the power to be 1 in this case, and in this case to be 1. Okay, so what you end up with is as you see here, the impedances ZA and ZB are 70.7 ohms, and this impedance and here are basically 50 ohm, and the resistor is 100 ohm. Now, let's say that I want this to be 1/3 of the power, and this is 2/3 of the power. That's, and as an example that I'm going to do right now in ADS. What you end up with is these power ratios, which we are familiar with, minus 1.7, minus 4.7. And that's in the last video. You've seen how we've done that for the T-junction. And you end up with these values in here. So you end up with low impedance lines for the ZA in here, while the ZB in here is a high impedance line, okay? I mean a low impedance line or a wider line, okay? So basically, that's what you do. It's very straightforward, small set of equations. And as an example, let's start with just the two-way power combiner with equal powers. And that's as a classic method of implementing them, just straightforward with a 90-degree band. Of course, this is this total length in here from the center and here to here is a quarter wavelength, and the same way here. And this was implemented basically. And now, before we do that, because the resistor in here, this resistor in here, it's a surface mount resistor. So what you really want to do is for the design, even though when you implement them like this in ADS, you really want to do, first of all, let's see, this is the classic one. So let's look at this. So basically this resistor in here, what you want to do is you want to make sure that you start with the dimensions of this resistor, this surface mount resistor. So what you do is whether you want to use 0402, 0603, 0805, 1206, depending on the size, you really end up, that forces you for the configuration of these our network in here. I mean, when you design it at first, regardless of the footprint of this thing works perfect. I mean, you can see here that it is basically minus 3 dB. I designed this for 12 gigahertz. And you can see the isolation. You can see the return loss is all nice and everything. But when you do the layout, the thing that you really want to make sure of is that in the layout, this is the resistor that I'm using right now. Okay, these are the dimensions of the resistor. You want to make sure that this resistor in here, you use it so that, because it's going to impact the response, the discontinuities in here. So really, even though you might say this design works beautiful, and even when you model it, but you really still need to model this in electromagnetic wave computation, EM. And that's what you would want to do. You come into this and you can, and I'll do that in next sessions, where you can actually put ports on this and attach an S parameter file that corresponds to the response of this resistor. And then you can actually get a response, which for sure is not going to be similar to the response that you get in here, like in this. Okay, so it's really important at the beginning that you get the resistors, and I did that in here. Let me just go back to this. This is, okay, here's a SMD resistor. So what I did is I got a few of these resistors in here. And if you look at the layout of these, so I'm going to go to the layout of these. And so what I do is you study these and you see which ones you want, and you have the dimensions of the length and width of the pad, and you have to really incorporate that ahead of time in your design. Okay. So let's close this and let's go further to the next. So that's how you do a classical to equal power Wilkinson divider. And a lot of you in the basic microwave courses have done this exercise. Now, the circled one, and a lot of times you get that is basically, let's go back to the shapes. If you look at the shapes, this one here can be nice in a lot of cases. And some of you may have done this already where if you want to do it rounded, of course, you gotta deal with a circle. And so for a circle, you start out because you need to compute the length of this line in here. The circle circumference is 2 pi r, so half of that is pi r. So what that means is you can actually figure out how to draw an arc in here and specify the radius for that. And that's basically for the rounded one. Is what we're going to do next, the next example. So let's do, so we did this classic, we did this. This is the rounded one. So if we open the rounded one, basically you can use these arcs to implement it. And what I did, in a lot of cases, people don't use this line in here, a straight line. And in my case, what I did is I used this because this gives me the flexibility to lengthen the quarter wave length so that I can tune this to any frequency that I want while maintaining this connection correct, okay? So I designed this for 12 gig, and you can see here that it is indeed working. So you get exactly the very same response. There is some kind of asymmetry focus when between the two lines, but that's fine. The layout of this is you end up with is basically this here. And like I told you, so what I did is I usually use a straight a line in here. I don't use these connected together like in a lot of cases. So I use asymmetrical arcs, and then I let this guy here be a flexible way to move this back and forth. Okay. So that's for this example. So very simple. Okay, so let's move on further. Okay, so let's, for the heck of it, let's just do a four-way splitter using this one in here. And that's what I did in here, of course. You can come in here and you basically, this is what I just did. So you just copy it twice at the output and run this thing, and that's what we do. And that's, let's go to this here and find where that for, okay, no, not this. Okay. This is the 8th. Okay, so like I said now, so we have, after we have designed, for instance, the unit cell of a two-way splitter, equal power in this case, we can go ahead and replicate this and put an extension line and some 90-degree bends, and we end up with whatever dimensions that you want to create. For instance, for 4 ones, you can see that it is right here, and the response is exactly like it is here, minus 6 dB. And show you that that's basically, this is the 8-way, so we're going to go to the 4-way, which is here. the four-way, of course, we just come in basically to the unit cell that we have designed in here, and we just copy it twice. We put one here and one in here, and if you run this, basically, you end up with very much very acceptable, very nice, same thing, except the input output as to one of the from 1 to 2 through to 1 of the 5, it's all minus 6 dB. Okay. You can go further than this. You can now, having this, you can actually copy the whole thing here twice, and you end up with 8-way splitter, 8-way feed network for an antenna, a linear antenna in this case, and that's basically what I did here. So I copied it. You can see this is the 1x4 that I just did. So I copied it and just pasted it here, attached ports, and kept the 2-to-1 in here. And if you run this, basically you end up with an 8-way splitter. And that's what you get in here, which is minus dB, 9 dB. Okay. And the layout for this, of course, is, let's show you the layout. This is the layout for this, and that's basically what you end up in here. So we can even view it in 3D. So basically, this is what you end up with. Okay, so this is a unit cell for 1x8, which can be used for planar antenna array designs, and we can do this repeated again basically for dual polarization. We can do this twice in 2 sublayers, 2 strip-line layers, one for the vertical and one for the horizontal. Okay, so let's get back to the presentation here. So we did this, we did this. Now you can do 16-way, and I'll do that at the end if there is time, so I'll come back to this. Now, this is, of course, for equal power. Equal power is basically the quarter wave transformer lines in here are equal. Okay, so but when you don't have equal power, let's say for instance I want to design this one so that I have 1/3 of the power on this port and 2/3 of the rest of the power on this port. Of course, we're really assuming in all these cases that we're lossless in these equations, which we are not lossless, but we're assuming the losses are going to be symmetrical between the port 1 and port 2 because the copper lengths are the same and copper image length. So in essence, we are assuming there's so what do you end up with? Unequal power divider. That's basically, as an example, let's do this. So which is what's in this sheet here. So you end up with ZA in here being a very narrow line. That's 100 ohm. And then the C and D, of course, you end up with these ones. And when you implement these, that's basically the shape you're going to get. Okay, doing them so you end up with asymmetrical type, and the response is exactly like it shows in here, which is minus 1.7 and minus 4.8, and that's basically what you end up getting from the calculator in here. That's what we intentionally wanted. That's 1/3 of the power and 2/3 of the power with these dB ratios. Okay, so let's go and see that one. Let me just minimize these so I can easier to view. So we're gonna go to example, equal power, equal, unequal power. So let's go this one. This is the implementation basically that I just did. So these lines in here were computed, the width was computed basically based on these equations in here, these results in here. Okay, so this is a 2-way asymmetrical power combiner where the power on one port is 1/3 of the power on the other port. So you end up with 1.8 and minus 4.8, okay? And that's exactly what we have designed it for, okay? In a lot of cases, of course, this still needs to be optimized, the lengths of these, so you don't end up with exactly where you want it for the 90-degree center frequency, but you can do that real easy. So again, The performance of this, as you can see, is exactly what we wanted on both of them, okay? This is exactly. All right, so this works out. Now, of course, in an antenna array, the ratios of these, to the power 1 to the power 2, that really is determined by the Taylor coefficients, the tapering coefficients that are these coefficients in here. So every one of these numbers demands that you have like for instance, let's take the order 8 in here. The two middle ones, they're 1, 1. Okay, but this one and the adjacent one, these two here on the right hand side, it's symmetrical. So what we do on the right hand side, we're going to do on the left hand side. So for the eighth elements array, for instance, the first Wilkinson divider is 1 and 0.84. That's the ratio between the powers. And the next one, which is the ratio of the powers, is 0.878 and 0.374. On this side here, they're the same, so you don't have to redesign them. So all you need to do is you come in here and plug these ratios. You end up with these impedances. Of course, the impedances in here, you need to convert that's the length. So basically, you end up going to the ADS utilities. There's the design guide utilities where you have in the tools you have the link calc basically, or you can go on the internet and basically find a microstrip calculator. There's a whole bunch of them. Microstrip strip calculator, for instance. You can see here that I looked at one already. So you end up with a lot of these calculators. So for instance, this one here I used for the substrate, they are 403 and for 36 ohms. So you synthesize that and you end up with this here, okay? And for 90 degree, of course, you end up with this length. So that's a starting point. You can either use that or either ADS synthesis to do that, okay? So that's the unequal power divider, two-way splitter, unequal power, which is this. Now, of course, when you look at this, now we really design these things based on the fact that we're driven by this. But when you end up with this, you look at this, that takes a lot of real estate horizontally. So what you need to do, you need to meander this line and this line and this line and this line to shorten it. And you can do that. And in that case, if you do that, you end up with basically a Wilkinson divider, which has the shape like these ones in here. You can see that, you look at how these meandering of these lines to accommodate to minimize the width and height of the board, okay? All right, so next, let's do one more, which is the three-way power splitter. I know a lot of people don't get into this situation, but three-way power divider in feed array networks for antenna array, it's very useful and very common, because a lot of cases you end up with an array, let's say a subarray of length 1/6, for instance. That's where you need a three-way splitter, okay? In a lot of cases, you end up with a three-way splitter is more efficient than deriving things. It's for the odd number of splits, okay? So the most common, here are some of the very common splitters that I've seen from the literature. This one here, which ends up with these two resistors in here. And because the lines in here, again, to squish them, you're always going to need to meander them, especially for the middle line, because this line, the upper one, Z1 and Z1 in here, this is all the same impedances in here and in here, and this for this particular design. The middle one, this one in here actually has a 90-degree band and has an additional length in here where the middle one doesn't. So the middle one is always going to be longer. So to get it's very, very important, of course, to get physically all the outputs and inputs the same length, so that there is no differential phase or differential time delay between the outputs. okay, relatively between the outputs. So you always need to meander, for instance, the middle line, to get the outputs to be all lined up, okay? And in this case, of course, you end up with 4 resistors, 4 surface mount resistors. The design equations for these are well documented in the references, so you can just Google out on IEEE, basically, publications, a 3-way splitter, and you get a whole summary of that. And I did run this example in here, so let me show you that. Let's close this, and let's close this. No, okay, so we're gonna go a 3-way splitter. Let's see which one is this. I did a few of them, so not this, that's a recombinant. Okay, for 3-way, let's look at this combiner in here. I mean, this splitter in here, 3-way splitter, according to this topology, this is pretty simple because all the impedances in here are equal. These are equal, and it needs 4 resistors. So, and this works out very well. Here's one implementation of this at 12 gigahertz. And so basically come in here, feed 50 ohm, and then we've got these 3 lines here, 3 lines here, and the output lines, of course. And you simulate this, you end up with this, which works out fine, which is 4.7. That's a 3-way combiner. And the isolation is pretty good for this because it's got these 4 resistors. The layout of this is, however, a little bit tricky because now, like I said, now the layout, this is all still in pieces right now. So basically, as you can see from the figure that I showed earlier, you really have to meander this to get it all lined up, okay? So you end up with having to do a lot of splitting this line and this line into pieces so that you can get them to line up, okay? So you can meander these as well. You can use multiple 90-degree bands that are rounded or that are edged, tapered. Okay, so I'll leave this as an exercise to do. Now, once you do this, of course, now you need to EM simulate this. You need to come in and attach boards to this and run EM simulator rather than linear simulator with S parameter based, because it's not anymore the same thing. But this is a good starting point. So I'll leave that as an exercise for my trainee students in my workshops. The next one is basically very similar, except on this one here, what it does, we end up basically using, I don't want to see a combination, but it's a different topology, okay? So this one here, and that's basically, oh, sorry, this one here I'm talking about. This one is also reported in the literature. And what it does, what we do here is we combine these. So this is really, as you can see, this impedance is the same as this impedance same as this impedance, while these impedances in here are also asymmetrical. Okay, so these ones here are asymmetrical, same one copied in here, okay? And then you get that one in there. That's the third here is basically recombination of these two. So this is, you can consider this part of the recombinant power divider techniques. And the impedances are all reported for these. So implementing this, we see that is here. So the implementation of this, of course, let me see if I have a picture of an implementation of this. I don't have it, but this also is tricky. Here is this implementation. Before I do that, let me just show you how it's done. So basically, you end up with this 2-way splitter. Okay, this line and this line are the same impedances. So this is symmetrical, equal power split. And then you end up with these 2 splitters, one in here, and you recombine these two basically using a T-junction into one, okay? And it works out pretty well. As you can see here, here it is. So you've got the marker in here is March 5 dB with a little loss, of course, but it works out well. Okay, now the layout for this is a little bit trickier. Like I said, you really need to, so this is, I've got part of it done here, but you end up getting stuck that these lines needs to be meandered, okay, to get this here to spread out so you can have the right dimensions. So that, because what's constraining you is these resistors in here, of course, the surface mount resistor. These surface mount resistors really, you need to make sure that the distance between the ports is good enough to get to be precisely so that you can place the resistor so that resistor pads is touching both outputs. Okay, the last technique for a three-way splitter also is one way you can get back to the basic classical Wilkinson divider. So basically you can split. First split is basically the same one that I designed here, which is to have 1/3 of the power in here and 2/3 over here, and then do two splitters and then recombine one of the two outputs that are 1/3 to get 2/3, and by doing that, basically you end up with 2/3 on all of the ports. So basically you take the signal, you split asymmetrically between 2/3 of the power here, 1/3 here, and then you split that 2/3 again to 1/3 and third, and then you got, of course, equal power division for three ports. Now, the only issue with this is this output here is, as you can see, it's shorter, much shorter than the two other outputs, and therefore you need to add an additional line to this so that you delay it. It's a delay line so that you equalize the path differences. And that's basically what these people did in here. This is one illustration from one of the fab houses of monolithic circuits. You can see here is the unequal power splitter, two-way, and this is the equal power splitter, which is this one here, where you split the 2/3 and the equally, okay? And that's basically what you do here. So this line in here, as you can see, they meandered this line to get to here, so that physically you have the same time delay between all three ports. And that's very important for phase array array antennas, because that could distort. If there are any mismatches in the paths in here, path lengths, you end up with distortion of the beam, and we don't want that, especially for the, now if you're doing beam forming, of course you can always correct for that in the beamformer states. That's another issue that I forgot to mention. Now we're really tapering, so therefore we're really putting a weight on every element in the array. This is really what it is. It's a fixed, static, one state beamforming essentially, but we're doing it with just amplitude weights. We're not messing up with the phase. So in case of beamforming, somebody might say, why don't we lump it into the beamforming weights in there? So all the Taylor and Chebyshev weights, they can be incorporated into the magnitude of the complex beamformer values. And of course, you can do that. However, you really lose the resolution, because then you end up with one weighting over another weighting, which probably not nice. So this is probably, you still want to do tapering statically better than doing it beamforming. And a lot of cases you get antennas arrays where they're not really beamforming, like in case of 5G and 6G panel antennas, okay? A lot of them, you get a fixed beam to cover a certain sector, but still though, you want to control the side lobes, therefore you resort to the tapering. Now, one more case on the, so this can be easily done, easily implemented. That's not a problem. We did implement this part and we implemented this part, so we can go back and just copy and paste this together and check how it works. The other one is similar to this, where we can use, and instead of using an equal splitter on this output, we reverse around and we say, let's start out with splitting the power equally, and then doing two asymmetrical splitters that are like this, where they, I mean like this, sorry, where they do the power splitting 1/3 on one side and 2/3 on the other side, and then you're combining. So we end up with the power splitting halfway, so equal power split on here, and we come to the half, and we split it basically. We split it using 2/3 and 1/3 ratio. That's what we designed here, basically, these ones here, okay? And when you do that, now you end up with basic 2/6 in here, 1/6 of the power in here, 1/6 is here, and 2/6 in here. Now, 1/6 and 1/6 power, recombine these together, and you end up with 2/6. Now, with that, really, all three ports have 2/6 of the power at the input, and that's really 1/3 of the power. And that's basically reported here by this. I think this was patented for a while by Raytheon for a number of years, and then the patent got out publicly, and basically it's not anymore registered, so you can do this implementation. And the layout basically is similar to this, so basically very much like this, except it's the other way around. Okay, so let's do this here. That's the recombination, and I just want to show you this example. Okay. So get to that. That's right here. So this is it right here. So the first thing we do is we split the power equally, and you can see this is 50 ohm, this 50 ohm output. And then we come back here, and we have two splitters, one in here and one in here. And these are the asymmetrical 2/3 of the power, 1/3 of the power splitters. So this is really here is basically, this is 2/3 in here, and this is 1/3 in here, okay? And this way, we have another one as a combiner, splitter turned around, which is a combiner in this case, and that's what we have in here. And this works very well too. Of course, that's it right here. You can see that all three ports have the same amount of power. Now, the only issue with this is the layout, of course, is a bit tricky, because what you need to do in the layout, you need to meander these lines. As you can see, you end up with the middle one is because it's pushed outward, and it has an additional this one here. So we really need to go back to these lines and increase the length of these so that it's up to here. Meantime, we need to squish this further in so that we can get this to be similar to this shape. As you can see here, you see that there's an additional line in here, an additional line in here, so that the face matches with this additional path that is here. And you need to meander the lines a little bit. So this could have been meandered even, and these ones in here could even got squished smaller. Okay, so this is what we've got. So now with this, we can go back to the arrays and really demonstrate how all of these arrays can be done in a two-way splitters if since you're doing them in a strip line. And of course, the resistor in that case would be used would be a thin film resistor using Tizer material on substrates. Okay, but it's good way it's mashed, it's isolated, but it's complicated fabrication wise and design wise. So that's why a lot of people end up with this using T-junctions, rather than unless of course they have a case where it's like this, where it's all can be done planar, and the resistors can be surface mount resistors. So again, now all of these things you really need to EM the simulations. This all these designs, we don't guarantee that you're going to get performance like this out of this, because this is based on S-parameter representation of these segments, where in the actual layout it's a little bit different. Okay, so you do need TE-Emmet. So this is what I've got, ladies and gentlemen. So again, this is Dr. Mohamed Nezami, thanking you for watching this. I would appreciate if you could subscribe to the channel and share it so that it appear more and more to others to benefit from. So this again, this was the third part in the array feed designs, array feed network designs for antenna arrays. And so basically, you can reach me at this number or this email. And again, for those of you that are in United States or Europe, my rate working out of Jordan, Garage, is very reasonable. I have short assignments, long assignments, medium assignments. You turn your concept to me, you give me your specifications, and give you fabrication files. Ready to go. And can even follow up with you in the design stages as well, in the prototyping. Again, this is Dr. Mohamed Nezami, thanking you again. Please look forward for the next 1 or 2 sessions, depending on what I will do next. Is basically the next thing we need to do is perhaps look at the Wilkinson dividers for multi-sections. That's an area where you can get a need for that when you're doing broadband designs for like cases for like EW and broadband Wi-Fi. Also the sequential phase, sequentially rotated feed networks. We need to cover the principles of that as well. Okay, until next time, I do thank you very much, and please come back again and watch. Thank you very much.